Okay, thank you. So we are the second team of National College of Viash, and we are Julia,
Robert,
and Alexia.
And we are going to show the Equide composability of polygons. All right, so we will talk about problem statement, our solution, particular cases, and conclusions. Okay, so the statement is this. Two polygons A and B of equal area are given. Can polygon A be cut into smaller polygons that rearrange from polygon B? To make a reduction easier, we will use the following notations. A can be transformed into B, which means that A can be cut into smaller polygons which rearrange from B, and A cannot be transformed into B, which means that A cannot be cut into smaller polygons which rearrange from B. Example 1, we have A square width of side of 2, and B a square with side 3, and A cannot be transformed into B. For the second example, we have A rectangle with sides of length 1 and 4, and B a square with sides of length 2. And A can be transformed into B as shown in the pictures under. Okay, so here are some key observations. If A can be transformed into B, then B can also be transformed into A. If A can be transformed into C and C can be transformed into B, then A can be transformed into B. And from these two, we get that if A can be transformed into C and B can be transformed into C, then A can be transformed into B, and we will use this later on. The actions of cutting and rearranging do not affect the area of the initial polygon. So, in order for A to be able to be transformed into B, it is absolutely necessary that the area of A is equal to the area of B. We will prove, therefore, that given two polygons A and B of equal areas, there is a way to cut A into smaller polygons that rearrange from B. So, here are the steps that we will present. First one is that polygon A can be cut into triangles for any given polygon. The second one, any given triangle can be cut into smaller polygons that rearranged can form a rectangle of equal area. Third one, any given rectangle can be cut into smaller polygons which rearrange from a rectangle with one side of length 1 and of equal area. And four, all these rectangles with one side of length 1 can be put together to form a bigger rectangle C with one side of length 1 and of the same area as A. According to all these steps, we can say that A can be transformed into C for any polygon A. B is also a polygon, so B can be also cut into smaller polygons that rearranged from rectangle C prime, a rectangle with one side of length 1 and the same area as B. Because A and B have the same area, it means that C and C prime are actually the same rectangle. So we will use the thing that we proved before. If A is can be transformed into C, B can be transformed into C, and we get that A can be transformed into B.
So the step 1 of our solution consists of the triangulation of a polygon. So for a convex polygon, it can be cut into triangles by choosing a vertex and tracing all of the diagonals which start from that vertex. For a concave polygon, it can be cut into convex polygons, for which we repeat the previous steps mentioned. So step 2 of our solution consists of transforming any given triangle into a rectangle. So the first step is transforming triangle ABC into rectangle BCYZ. For that, we use the following notations. X and Y are midpoints of line segments AB, respectively AC, and D is the line parallel to AC that goes through B, and Z is the point of intersection of D and XY. And the figure that we added in this slide basically represents how we can make a parallelogram out of the triangle. And the next step, in order to form a rectangle from that parallelogram, so we will transform the parallelogram ZYCB into a rectangle ZZ prime YY prime, in which Z prime is the foot of the perpendicular from Z to BC, and Y prime is the foot of the perpendicular from Y to BC.
Step 3, we will prove that any rectangle can be transformed into a square with the same area, which also means that any square can be transformed into any rectangle of the same area. From these two observations, it concludes that any rectangle can be transformed into any other rectangle of the same area. So any rectangle can be transformed into a rectangle of the same area and with one side of length 1. We will consider the rectangle A prime, B prime, C prime, D prime with side lengths A prime and B prime. A prime smaller than B prime, and the square of equal area x, y, z, t, with side length of C equal to the geometric mean of A prime and B prime. We will transform the rectangle A prime, B prime, C prime, D prime into the rectangle A, B, C, D with sides of lengths A and B with the following properties. A is smaller than B, and B over C in a specific range of values. We need that property in order for the proof to look as simple as it does. If the ratio is not in that range of values, it will either not work with this method or be a lot more complicated. But we can use some simple transformations to modify B while C remains constant. And ABCD is that rectangle with side lengths A and B that respects all these properties. And we split both the square and the rectangles into different polygons. And we show that we split them into different polygons that can be shown to be congruent. For example, on this image, the polygon EFIKJ is the same as GNOZF. And for every polygon that we cut ABCD into, it has a correspondent in the polygons of X, Y, Z, T. So to summarize and to show the full method for transforming any polygon A into any polygon B, we first cut A into triangles. Then we transform each of those triangles first into a parallelogram and then into a rectangle. We transform each of those rectangles into a square of equal area, which we then transform into a rectangle with the same area and a side of length 1. Then we put all those rectangles together to form a rectangle of with area equal to A and with a side of length 1. We repeat steps 1, 2, and 3 for polygon B, and then we do them in reverse order on polygon C. And thus we have transformed polygon A into polygon B. And here we have some specific cases. For example, here we have a square and a triangle, a square and an equilateral triangle of equal area. And this is the minimum number of pieces in which we need to cut one polygon in order to transform it to the other. And we have a few examples. This one is particularly interesting because of the rotational symmetry that it has, which isn't that often in this situation. You can see this one is very complicated. This one also has a nice symmetry down the vertical line.
So now we can present our conclusions. So we proved that any polygon can be cut into triangles, and any triangle can be dissected into polygons which rearranged form a rectangle. Any rectangle can then be transformed into a square of equal area, and any square can be transformed into any rectangle of equal area. In other words, any rectangle can be dissected into smaller polygons, which after a series of rearrangements form another rectangle of equal area. Therefore, any polygon can be transformed into another polygon of equal area. In conclusion, this is the procedure, not necessarily the most efficient, to dissect a polygon A into smaller polygons, which rearranged form polygon B. And thank you for your attention. If you have any questions, please
thank you for the presentation. It was really clear. I'm just having a look if there is some question in the chat. I've got a question in the list here. We're going to have a question from here.
Hi, can you hear me?
Do you hear us? Yeah, can you hear? Okay. Which main question?
So that's right. We spoke about the optionality of the transformation and said that. Okay, it's really bad. Let's try it in the chat.
You try, yeah. So the question is
no, we haven't tried to estimate the minimum number of steps needed, but it differs from situation to situation.
okay, thank you for the answer. As we are really late, we're going to do the break now, and we start again 4:04 with the group of two. Thank you very much.